Good morning, students, and welcome to the technical class on transformer design. And we shall be discussing some numericals on transformer design. Okay, let us continue to solve some machine design numericals on this subject. So, students, previously we had done one question. We had done this question: estimate the reduction in volume expressed as percentage of original volume of iron core and conductor in a transformer, and we are replacing the hot rolled silicon steel lamination with the cold roll grain oriented silicon steel. Okay, but and we got that by replacing the hot rolled silicon steel lamination with CRGO, we can get approximate around about 33.3% reduction in the net iron area or saving in the iron and 18% saving in the copper. Okay. Today we shall be discussing an equation. Expression was that show that the output of a three-phase core-type transformer is Q equal to in kVA 5.23 into frequency into Bm HD square HW into 10 raised to the power minus 2 kVA, where F is the frequency in Hertz and Bm is the maximum flux density in Weber per meter square. D is the effective diameter of core in meter, and H is the magnetic potential gradient in limb ampere per meter. HW is the height of limb window in meter. Right. So you can just note down this question. We have to use the output equation of a transformer to solve this question. Okay, so this is the equation which we have been using. kVA output of a three-phase transformer is given by Q equal to 3EI. Okay, kVA output of a three-phase transformer Q is equal to 3EI into 10 raised to the power minus 3 kVA. Q is equal to 3 into 4.44 into frequency into maximum flux into number of turns T into I current into 10 to the power minus 3 kVA. Where we can also write our Q equal to 3 into 4.44 into frequency into maximum flux density Bm into area of iron into number of turns into the current into 10 to the power minus 3 kVA. In core type transformer, each limb has one primary and one secondary winding wound on it. So total MMF over one limb should be equal to 2 times number of turns into the current I. Okay, so you can just note down this expression in your notebooks. I hope the screen is visible to you. If you have any doubts, you can just write down on the chat box, and you can also write your roll numbers in the chat box for attendance. Okay, so now we know that the potential we know that the magnetic the magnetic potential gradient magnetic potential gradient H is actually given by magneto motive force divided by height of the limb. Height of limb, which is actually equal to the magnetomotive force will be equal to 2 times number of turns into current I, which is divided by height of the limb, which is given by HW. Or we can write that number of turns into the current is equal to magnetic potential gradient into height of the window, height of the limb divided by 2. And we also know that area of the iron is basically equal to pi by 4 into d square. So we can substitute these values for Q, and we can actually get our expression Q is equal to 3 into 4.44 F into Bm into pi by 4 into d square into H into HW by 2 into 10 to the power minus 3, which can be again equated to our required expression 5.23 into frequency into Bm maximum flux density into H d square HW into 10 to the power minus 3 kVA. Right? So this is our answer. Okay. So this was an easy question, and just you had to remember the expressions, the formulas for the magnetic potential gradient, and the formula for the magnetomotive force, number of turns and current, and the net iron area of the core. And using all these formulas, you can solve your question. So I hope you understood, and this was a quite an easy question to solve, right? So let us move towards the next question. Okay, from AK Shani. We are basically doing all these questions from AK Shani only. So you can also refer the book at your home. Okay, so the next question is calculate the kVA output. Calculate the kVA output of a single phase transformer from the following data. By core height divided by the distance between the core center is given as 2.8. The ratio of the core height and the distance between the core center is given as 2.8. The ratio of the diameter of circumscribing circle and the distance between core center is given as 0.56. The ratio between net iron area and the area of circumscribing circle is given as 0.7. Current density is given as 2.3 ampere per millimeter square. Frequency is given as 50 Hertz. Distance between core center is given as 0.4 meter. Window space factor is given as 0.27. Flux density of core is given as 1.2 Weber per meter square. Okay, so these are all the details which are given in the question. You can just note down this question in your notebooks, and then we shall start solving this question. What we have to find? We have to find the kVA output of a single phase transformer from the following data, where ratio of core height by distance between core center is given as 2.8. Diameter of circumscribing circle to the distance between core centers given as 0.56. The ratio of net iron area to the area of circumscribing circle is given as 0.7. Current density is 2.3 ampere per millimeter square. Frequency is 50 Hz. Distance between core center is 0.4 meter. Window space factor is 0.27. Flux density of core is given as 1.2 Weber per meter square. Okay. So we have to apply all the formulas for the transformer, and you can just find the kVA output. It's an easy question. Okay, so let us move to the next sheet. Okay, so you can see here that distance between core centers distance between core centers D is given as 0.4 meter. Okay, and then we have the core height, which is basically also equal to the window height, core height or window height, because the transformer is a core type. Okay, so core height or window height HW is given, we can find out HW equal to 2.8 into 0.4, where 2.8 is the ratio between the core height and the distance between core centers multiplied by distance. So that is equal to around about 1.12 meter. Then we can just find the diameter. The diameter of circumscribing circle D will be equal to 0.56 into 0.4, where 0.56 is the ratio between the diameter of circumscribing circle to the distance between core center, and 0.4 is the distance between core center. So diameter of circumscribing circle D will be equal to 0.56 into 0.4, that is equal to 0.224 meter. And then we have width of window. Then we have width of window width of window WW is equal to capital D minus small d, that is equal to 0.4 minus 0.44, which is actually equal to 0.176 meter. Okay, that is the width of window, 0.176 meter. And then we have area of window, AW is equal to HW, the window height, into WW, the width of window. Okay, height of window into the width of window, that is equal to 0.112 into 0.176, that is equal to 0.197 meter square. Then we have the area of circumscribing circle, which is equal to pi by 4 into d square, which is equal to 0.0394 meter square. Therefore, we have our net iron area AI is equal to 0.7 into 0.0394, that is equal to 0.0276 meter square. Okay, so in this way we discovered all different parameters, and then we had to use this equation for the transformer, output equation of the transformer, which is given by Q equal to 2.22 into F into Bm into Kw into delta into Aw into Ai into 10 to the power minus 3 kVA. Okay, so just note down all these values, and then you can try to solve this. Okay, right. So I hope you might have solved this expression. Let us try to solve this together. Okay, so let's put the values in the expression. So we have the expression Q equal to 2.22 into F into Bm into Kw into delta into Aw into Ai into 10 to the power minus 3 kVA. So we can put the values in this expression. Q is equal to 2.22 into 50 into 1.2 into 0.27 into 2.3 into 10 power 6 into 0.197 into the area of iron, that is equal to 0.0276 into 10 power minus 3, and solving all this value, it will be around about 450 kVA, right? So that was an easy question. I hope you understood how to solve this question. We shall be doing more question like that in our next session. Okay. So for those who were late or they did not come, let us again go back to the question. And this was the question. Calculate the kVA output of a single phase transformer from the following data. And the following data was given. Core height by distance between core centers, the ratio is 2.8. Net iron area divided by area of circumscribing circle, the ratio is 0.7. Current density is given as 2.3 ampere per millimeter square. Frequency is given as 50 hertz. Distance between core center is given as 0.4 meter. The ratio between the diameter of circumscribing circle and the distance between core center is given as 0.56. Window space factor is given as 0.27. Flux density of core is given as 1.2 Weber per meter square. Okay. So to solve this question, what we did, we just applied some formula. Okay. And what was the formula? That distance between core center D was given as 0.4 meter. So we just found the height, core height or window height HW by multiplying the ratio of the core height by to distance between core center, that is 2.8 into 0.4. So we get 1.12 meter. The diameter of circumscribing circle D is equal to 0.224 meter. Width of window WH we got. Area of window also we got 0.197 meter square. Area of circumscribing circle also we got from pi by 4 into d square 0.0394 meters square. Then we got the net iron area AI equal to 0.7 into 0.0394 equal to 0.0276 meters square, right? And by putting all the values in the expression for Q, which is 2.22 F Bm kW delta AWAI into 10 to the power minus 3 kVA, we got our expression for Q, which was equal to 2.22 FBM kW delta AWAI into 10 to the power minus 3 kVA. Putting all the values in this, we got our output of the transformer is equal to 450 kVA. Okay, so I hope you understood this question, and we shall be doing more questions like that. Okay, thank you so much. You can just note down this expression, and you can also write your attendance into the chat box for attendance, and be attentive in the class, and you should attend your classes.